In this video, I'm going to show you a simple demonstration to illustrate conservation of angular momentum. Here I have a spice tray, so I can just give it a spin and you can watch it rotate. Now what I'm going to do is spin the spice tray again, but immediately after I spin it, I'm going to put this heavy weight down onto the edge of the spice tray, and we'll see what happens. I'll do that again. Could you see that when I put that heavy mass near the edge of the spice tray, the angular velocity decreased almost immediately? We're going to see if we can use conservation of angular momentum to understand why that happened. Before we get into the explanation of the demo, let's go over the basics of angular momentum. So let's say I have an object which is rotating at angular velocity omega. The object has moment of inertia I with respect to whatever axis it is rotating around. We say that the angular momentum of the object with respect to that axis is equal to the moment of inertia times the angular velocity. Conservation of angular momentum says that if you have a group of objects and no outside torques act on that group of objects, then the total angular momentum of that group of objects is constant. Or we can say that if we have a process where no outside torques act on that group, the total angular momentum of the group at the beginning of the process equals the total angular momentum of the group at the end of the process. Now let's come to that demo that I just showed you. In the initial situation, I had that spice tray, and the spice tray was rotating at some relatively fast initial angular velocity. Then I put a heavy object near the edge of the spice tray. Let's call that the jar. And almost immediately after I placed that jar near the edge of the spice tray, the angular velocity became much smaller. How can we use conservation of angular momentum to understand the experiment? Well, first let's talk about the moments of inertia of the tray and the jar. Remember that the moment of inertia of an object is the resistance of an object to change in its rotational motion. So let's say that the moment of inertia of the tray with respect to rotation around this axle here is I sub t. And let's say that the moment of inertia of the jar with respect to rotation about this axis here is I sub j. In the initial situation here, what would be the total moment of inertia of everything which is rotating here? Well, in the initial situation, the only thing which is rotating is just the tray by itself. So the moment of inertia in the initial situation would just be the moment of inertia of the tray. How about the final situation? In the final situation, both the tray and the jar are participating in the rotation. So the moment of inertia in the final situation would be the moment of inertia of the tray plus the moment of inertia of the jar. Now let's apply conservation of angular momentum. Conservation of angular momentum applies if you have a group of objects and no outside torques are acting on that group of objects. In this problem, the group of objects is the tray and the jar, and although those exert torques on each other, there are no outside torques, and so we can say that the total angular momentum in the initial situation equals the total angular momentum in the final situation. What would be the total angular momentum in the initial situation? We can write that as initial moment of inertia times initial angular velocity. What would be the angular momentum in the final situation? We can write that as final moment of inertia times final angular velocity. Now, let's compare the moment of inertia in the initial situation with the moment of inertia in the final situation. The moment of inertia in the initial situation is smaller because the only rotating thing here is the tray. The moment of inertia in the final situation is bigger because it includes the moment of inertia of both the tray and the jar. So as we go from the initial situation to the final situation, the moment of inertia got bigger. How can the product moment of inertia times angular velocity stay the same if the moment of inertia got bigger? Well, the angular velocity must have got smaller. So we must have started out with a bigger initial angular velocity and ended up with a smaller final angular velocity. So to sum up here, as we go from the initial situation to the final situation, the moment of inertia got bigger. So in order to conserve angular momentum, the angular velocity must have decreased. In the next video, we're going to do a computational problem based on this exact same scenario.